This week we talked about three new things. We talked about how we could interpret the derivative as a rate of change. We talked about the chain rule, and we discussed the definition of the derivative and how that relates to continuity. Well, are there any questions before we start? Okay. There is a homework assignment this week. It has a few questions. I tried to make it a little shorter since it's just 1 week of information. So number one, we have 8 questions where we're taking derivatives. Now we are using chain rule. And with some of these, I will write out the substitution. With some of them, I will not. With this one, I will. So here we want dy dx, y equals x to the 4 minus 3x plus e to the x, all raised to the 4th power. So here we have something to the 4th. Well, if we let u be that something we're raising to the 4th, well, then we can apply the chain rule because, well, we can take the derivative in or by applying the chain rule. Because y now equals u to the 4th, we can find the derivative of y with respect to u using our derivative rules. We can find the derivative of u with respect to x using our derivative rules. So here, dy du is 4u cubed. Here, du dx is 4x cubed minus 3. Derivative of e to the x is itself. So we have our dy du and our du dx. We can now multiply them to get dy dx. Equals this first one times the second. So what do we have? We have 4u cubed times 4x cubed minus 3 plus e to the x. U equals what? So equals 4 times x to the 4 minus 3x plus e to the x, all cubed. So we do want to get rid of u from our final answer because we can write u in terms of x, and we want this in terms of x. Times 4x cubed minus 3 plus e to the x. Any questions about this first one? So notice our original function is a function to the 4th. We could take the derivative without writing out this substitution by recalling the derivative of something to the 4th is 4 of them to the 3rd, but then chain rule says multiply by the derivative of this quantity, which is 4x cubed minus 3 plus e to the x. And of course, up here we have the details for why we get that. So any questions about 1a? One b, log of cosine of x. Log of cosine of x. So right here, we have log of cosine. We have log of something, the natural log of something. Well, we know how to take the natural log, the derivative of a natural log of something. So let's let u be that something. If we let u be that something, y is now a function of u. We can take the derivative of y with respect to u using our derivative rules. We can take the derivative of u with respect to x using our derivative rules. So dy du, derivative of log u with respect to u, 1 over u. This is rule 9 in that page. No, it's rule 8 in the document derivative rules. du dx, well, derivative of cosine x is on page 3 of our derivative rules. Derivative of cosine x is negative sine of x. Well, now, to find dy dx, we just multiply these and get rid of u. And what do we have? We have 1 over u times negative sine of x. So what is that? U equals cosine of x. So we have negative sine x over cosine x. The directions probably, oh, they don't say don't simplify. The directions generally say don't simplify. And that's largely because of things with like factoring and quotient rules. I don't want you worrying about that. But here, it is worth simplifying this, especially for those of you who are going to take Calc 2. This one does simplify conveniently to negative tangent of x. You know, so, and I would not take off for negative sine x over cosine x, but you know, that it is worth observing, especially for those of you in Calc 2. It is worth observing. Not in Calc. Those of you who are going to take Calc 2, definitely worth observing that negative tangent of x comes, or is what this simplifies to. Any questions about this one? It may also be worth noting something in your notes that I might mention this in week, I'll probably mention it in week 12, this exact problem. So any questions about 1b? Okay, 1c. Y equals e to the 3x, tangent of 5x. Well, notice here we have a product rule. So if we're going to use the product rule, well, we need to eventually take derivatives of both of those. So I'm going to write the answer up here, and I'm going to do some side work down here. So the answer for this will fit on one line, but I am going to do side work. What side work am I going to do? Well, we eventually have to take the derivative of e to the 3x. We also eventually have to take the derivative of tangent of 5x. So I'm just going to do both of those on the side. Some mathematicians may not like using y as that, and then on the side using y as this. I'm okay with that. That's okay. That's fine with me. Side work. So here we're going to do the derivative of e to the 3x. Well, we don't have a rule for e to the 3x. We have a rule for e to the x. So let's let u be the exponent. Then dy dx is dy du. The derivative of e to the u is itself, times du dx. Derivative of u with respect to x is 3. And this simplifies to what? 3e to the 3x. Any questions about that first part of side work? So we found the derivative of e to the 3x, which we're eventually going to need up here. We got 3e to the 3x. Any questions about that? I will lower the camera a little so that that shows up. So notice we have e to the 3x. Derivative of e to the 3x is itself, but then you apply chain rule multiplied by the derivative of 3x, which is 3. So you could also have observed that that way. And I will make that observation for this piece of side work. So over here, you could do the details, let u equal 5x, and go from there. I'm just going to write over here du dx? Well, we have a tangent function. The derivative of any tangent function is a secant squared function. Leave the 5x alone. Multiply by the derivative of the 5x, which is 5. So if you want the details, let u equal 5x, dy du secant squared u, du dx 5. The u substitution for this one is very similar to that one. Any questions about this second piece of side work? Okay, so now that we've done the side work, we can find our original derivative by using these and the product rule. So the derivative of this product up here is the derivative of the first, which is down here, times the second, plus the first, which I'm going to write over here for organizational purposes, plus the first times derivative of the second. So I'm going to put the 5 out front. So here we have derivative of the first times the second plus the first times derivative of the second. And again, you don't have to simplify it. Like you can, pull out any of the three. Don't worry about that. But any questions about this one? Okay. 4. Something else I wanted to say about that one. Maybe not. X times the inverse sine of 7x. Well, we also have rules for the derivatives of inverse trig functions, unproven rules. In week, whatever next week is, week 8, the first lecture is going to be on the derivative of inverse functions, and we do prove the derivative rule for the inverse sine of x. And the others are similar. But here, we have, again, x times something else with x's. So we have two things multiplied. We're going to need a product rule. So let's fill that in, see what we get. Derivative of x is 1. 1 times the second, plus the first, which is x. I'm going to write it like that, times derivative of the second. So we need the derivative of the inverse sine of 7x. So how do we do that? Well, we do it up here. And in your work, you don't have to mark off side work. This is more for board organizational purposes. Board organization purposes. Well, sine inverse of 7x, we know how to take the derivative of sine inverse of x using our page with 22 rules. Or 4 pages with 22 rules. So we can let u, in this case, be 7x. Then dy dx is dy du, du dx. What's dy du? Well, the derivative of an inverse sine of u is given on page 4 of our derivative rules document. 1 over 1 minus u squared, all under square root. Du dx, derivative of 7x with respect to x is 7. So dy dx in our side work would be those two multiplied. And I'm not going to write that out. I'm just going to write it down as part of this answer. So we have derivative of x is 1 times the second plus the first times derivative of the second. So we have this first thing times this thing. So that equals 7 over So you multiply these, what do you get? I guess I will write it up here. You get 7 over 1 minus u squared, so 7x all squared under a square root. And I just simplified 7x all squared to 49x squared. But the derivative of inverse sine of 7x is given by that. So we need to throw that down here in our product rule. And then that x is also there from our product rule. Any questions about part D? Let's see, what else do we have? Any questions about part D? So there are a lot of these where, we have in part C, we have a 3x and a 5x. Part D, 7x. The next two, we have 4x's. Those types of things do show up frequently. They turn a regular derivative problem into a slightly more interesting derivative problem. So I did put a bunch of them on here. E and F. Debating if I want to do these two at the same time or if I want to do them separately. Yeah, let's do them separately. Cosecant 4x. I guess the question is. So the details of the chain rule are very useful for making sure you're not overlooking something. The details meaning writing out the u substitution and going from there. They are particularly useful, I think, for a problem like this. And I'll show you why. We have a cosecant function. The derivative of cosecant x, remember, is given by negative cosecant x, cotangent x. So let's use our multiplying by derivatives of inside observation up here. We have a cosecant function, derivative of cosecant is negative cosecant cotangent. So we have a negative. Cosecant 4x, cotangent 4x. But then we need to use chain rule. How do we use chain rule here? Well, there's an incorrect way and a correct way. Let's use a different color for the chain rule here. Well, you might observe we have a negative cosecant of 4x. So there's a something in there, a 4x, and a cotangent of 4x. Derivative of 4x is 4. Derivative of this 4x is 4. Which would simplify to negative 16 cosecant 4x, cotangent 4x. So right here, I got that by doing our multiply by derivatives of inside quantities and going from there. So this first 4x gave us that 4, and that marker's almost out of ink. This next 4x gave us that other 4. This answer is incorrect. And it's a very easy mistake to make. I made it when I was learning these. I made this mistake, and then I looked at the details of the chain rule and realized exactly why only 1 4 shows up, despite there seemingly being 2 inside quantities. So let's look at the details of the chain rule. Maybe I'll put an X through this. X. That is not correct because there's technically only one 4x that we're dealing with, even though 2 show up. So let's look at the details. Let u equal 4x. So then dy du. So if u equals 4x, y is cosecant of u. dy du, negative cosecant u, cotangent u, du dx is 4. Only one 4, because there's only one 4x. And now multiply these two together. And what do we get? Dy dx. I'll pull all the constants out front. Negative and 4 cosecant of u, cotangent of u. And u equals 4x. So only one 4 does show up. Even though it looks like with the multiplying by derivatives inside ours, it looks like 2 4s could show up, but notice in the details, only one 4 shows up. Any questions about this one? Camera's still not low enough to raise. So any questions about this one? So only one 4. Let's see if this other marker has more ink. 5, not 5, 6. Y equals the square root of cosecant of 4x. Well, the square root, remember, can be rewritten with an exponent, and then we can apply power rule. So here we have cosecant 4x to the 1/2. Well, how do we take the derivative of cosecant, or of something, to the 1/2? Well, it's just like in problem A. This question F is really just like combining problems A and E. But I will write out the substitution. Well, yeah, I will. Will I? Yeah. We have a function all to the 1/2. So let's let u be that entire function that we're raising to the 1/2. So that y is just u to the 1/2, and we can take dy du using using power rule. So dy du, derivative of u to the 1/2, I'll just leave it as half u to the negative half. You don't have to, if you want, you could write it 1/2 root u. I'm going to leave it as half u to the negative half. That's dy du. Du dx, notice u is cosecant of 4x. We already found du dx in problem in part E. I'm just going to say part E gave us du dx. It's that quantity rectangled at the bottom of the board. So now dy dx is these two multiplied. U equals that, cosecant 4x. We're raising it to the negative half, times du dx. So times negative 4. So we have our dy du times our du dx. Any Well, before any question, this does simplify it a little bit actually, because the 4 and the 2, but also the cosecant simplify it. You don't have to simplify this, even though, you know, I look at the 4 and the 2 and think they should just go away. But, you know, for a problem like this, you can definitely leave it like this, you know. Simplifying derivative computations is frequently not useful for understanding derivative computations, which is what we're trying to do in part A, or part A, number 1, even though, you know, it does simplify. For those of you who tried simplifying it, it does equal -2 cotangent 4x over root cosecant 4x. Oh, no. The root is in the top. So it equals -4. I'll just tell you, if you wanted to simplify, I'll put in parentheses, it equals -2 . You certainly do not have to simplify, but if you wanted to, it would equal that. Half of this would cancel with, or half of this would cancel with that, and you're left with half of it. But again, don't worry. It's more important, especially for a problem like this, to see how we're using the chain rule. The derivative of y with respect to u equals this first piece. Derivative of u with respect to x equals that second piece. Any questions about part F? Okay. Part G, cotangent x squared log base 5. Cotangent x squared log base 5, 4x plus 1. So here we have a quotient. We're going to need a quotient rule. So I'm going to start doing the quotient rule now. Then I'm going to fill in other information in a moment. Derivative of a quotient is bottom, derivative top, minus top, derivative bottom, over bottom squared. So let's write some of that out. So what do we have? We have bottom. I should have left a little more of a gap here. I guess I will. So we have bottom. We need derivative of the top. I'll leave a gap for that. Minus top, derivative bottom. We need the derivative of the bottom. I'll leave space for that. All over bottom squared. Logarithm all squared. So now we need to do the derivative of the top and the derivative of the bottom and fill them in our numerator. So let's do that as side work. Let's do the first one first. Again, I'm using y 3 different times. That's fine with me. Cotangent of x squared. Well, the derivative of a cotangent function is a negative cosecant squared function from our derivative rule. So the derivative of a cotangent is a negative cosecant squared, but then we need to multiply by the derivative of x squared, which is 2x. It's a lot of 2's. Block off the side. These markers don't last long at all. Sometimes they last longer if you put them upside down in your pocket for a few minutes. So for this first piece, cotangent x squared, you could write out your u substitution, u equals x squared, dy du, negative cosecant squared u, du dx, 2x, multiply them together, you get negative 2x cosecant squared of x squared. And where do we need that? Well, we need it up here in front. negative 2x. So I'll just write it like this. That's not how you spell cosine. So I put the negative 2x there, and I put the other thing there. You could, again, you could, write log 4x plus 1 base 5, and then times negative 2x cosecant squared x squared if you want. I just wrote it like that. Any questions about that first part so far? Okay, so now we also need the derivative of the bottom. So we'll do that as side work. Y equals log of 4x plus 1 with base 5. Well, I'm going to write out the details for this. We have a derivative rule for logarithm with a general base. So let's let u be, in this case, 4x plus 1. So what is dy du? Well, dy du, where do I have room? I think this is going to take 2 lines of work. Yeah, I'll just write, so dy du, log of u with base 5. Well, the derivative rule there is that the derivative of log of u with base 5 is 1 over u times the natural log of 5. What's du dx? Well, we have 4x plus 1. Derivative of 4x is 4. Derivative of 1 is 0. So we get 4 is du dx. So what's dy dx? I'll write it over here. Those two multiplied. So what do we get? We have 4 over u times the natural log of 5. And notice we're multiplying all of u by the natural log of 5. In other words, this right here is incorrect. You need to multiply all of u by natural log of 5. The details for this are quite similar to the details for b, except we have this extra constant in the denominator. But why did we do all this? Well, we did it so we could answer this question up here. So let's just put this quantity on this cotangent x, and I'm just going to write it all as one fraction. 4 over 4x plus 1 natural log of 5. So we have bottom, derivative of the top, minus top, derivative of the bottom, over the entire bottom squared. I'll simplify this. Any questions about this one? So there's a lot to keep track of in this one. What's the last one? Probably an exponential. Yes. Part H, that was cosine, not cotangent, right? That's part H, 3 to the x cosine of x. Well, with general exponentials, I generally do like to write out the substitution because I think there's a lot to keep track of with them. Does anyone not want me to erase this answer for part G yet? Okay, then I'm going to start erasing. So our derivative rules, we have a derivative of a general exponential rule. So let's make a substitution that reduces this to a general exponential rule. In other words, we have all those x's in the numerator. Let's make them a u. So here, u is x cosine x. So we're left with 3 to the u. What's dy du? Well, we have a rule for general exponentials. Derivative of a general exponential is itself times the natural log of the base, which is 3. So we have exponential and logarithm rules, natural exponential and natural logarithm rules. The only difference between them and their general rules are an extra constant. So we have dy du is given by that. What's du dx? Well, to find du dx, notice we have a product. So we'll need the product rule. Derivative of x cosine x, derivative of x is 1. So we have 1 times cosine x plus the first, which is x. Derivative of cosine is negative sine. So that plus becomes a negative. So we have derivative of the first, which is a 1, times the second, plus the first, times derivative of the second. Any questions about these two parts of the chain rule? Well, then dy dx is what? This times that. So 3 to the u, natural log of 3 times du dx. So we have 3 to the u, log u, times du dx. And notice, we went through all of this work and have the wrong answer. Because we didn't multiply by everything. You need to multiply by all of du dx. So now it's correct. So any questions about that one? Any questions about anything in part or number 1? Now, these types of computations, I think, do require a good deal of practice. So, in the textbook, I think this is section 3.6 in the textbook. Actually, it might be better to go to the chapter 3 review because they combine all of the rules. So the chapter 3 review will have several chain rule questions you can practice. Several more. Number 2, find the second derivative. So, well, we need the second derivative, so we need the first derivative, then we need the derivative of that. So what do we have? E to the 3x plus tangent x. You can see that I may have come up with this problem by copying and pasting 1a, or 1c. What was it? E to the 3x plus tangent x. Find the second derivative. This is actually a much, much more annoying computation than it had to be, because I made that a tangent x. The second derivative of tangent x is a really obnoxious derivative, I think. But let's go through it. From part C, one part C, we found the derivative of e to the 3x. It was 3e to the 3x. Because the derivative of e to the x is itself multiplied by derivative of the exponent. We also saw derivative of tangent x was secant squared of x. So we have our first derivative. Any questions about the first derivative? f prime prime, the next derivative. Well, how do we do the next derivative? Well, remember, the constant carries through. So this 3 is going to carry through, and then we need the derivative of e to the 3x. Well, the derivative of e to the 3x is 3e to the 3x. But then there's another 3 on it. Marker hole for me. There's another 3 on it. So we have 3 e to the 3x and another 3, which makes a 9 e to the 3x. Any questions about that first part? Okay. The second part. Two secant squared x tangent x. Where did that come from? Well, I'll show you the details in a moment. I wrote that there in case some people already did this and want to check their answer before we go over the details. But where does that come from? Well, I'm going to do that as side work. I'm going to let y, I'm going to write out the chain rule for y equals secant squared of x. This right here looks like a secant function, but it's something a little more. It's a secant squared function. It is a function squared. It is something squared. What is it squared? It's secant of x all squared. This is a function squared. First important observation, a function squared. How do we take the derivative of a function squared? Well, here we're going to let u be that function, and we're going to square it. In other words, we're going to let y, or let u equal secant of x, so that y is u squared. Any questions about this so far? It's a function squared. Well, now dy dx, well, dy du, what's that? U squared, derivative of u squared with respect to u is 2u to the first, so 2u. We'll get rid of u in a moment. So dy du is 2u. What's du dx? Well, u is secant of x. Derivative of secant we haven't seen yet today. Derivative of secant, secant x times tangent x. So we have dy dx 2u secant x tangent x, u equals secant x. So get rid of the u. 2 secant x, secant x, secant x, secant x is also known as secant squared. So we do have 2 secant squared of x times tangent of x. If I left the 5 there, that would have been really annoying to organize rather than just well, I guess this is a record. I don't remember the adverb I used to describe that earlier. Any questions about this one? What was this, number 2? In doing chain rule questions, I always find trig functions raised to powers the most difficult to keep organized, which is actually why I drew those parentheses as large as I did. So any questions about this one? I believe in lecture we did something with cosine to the 4th. That's a similar argument to this. So these first 2 covered chain rule. The next 2 cover some of the other things we covered this week. Now, the differentiability lecture, I mentioned in the email I sent. I did record that 3 weeks ago. So in the middle, it may have seemed strange when I said by lecture 5.2, when lecture 5.2 didn't exist. But, you know, I forgot about the off day, so I made the necessary adjustments. I am prepared for the next off day, which is April, whatever. It's a Wednesday. April 27th, I think. No, 28th. Oh, speaking of which, there is an updated syllabus, which I didn't email you about. I just changed a couple of the sections that we're covering for future weeks. And that's the only thing that's different. That's posted. So where were we? Number 3. So sketch a graph of f of x, show f of x is not differentiable at x equals 0. So in the lecture, differentiability, we discussed the relation between differentiability and continuity. And we discussed one of their relations in detail. We stated the other, that all differentiable functions are continuous. But in showing that all continuous functions weren't differentiable, we had 3 types of counterexamples. We had a corner, marker's terrible. We had a corner. The derivative does not exist at a corner using a slopes of tangent line argument. We covered that one in detail with the absolute value of x, showed using the definition of the derivative that the derivative didn't exist there. The second type is something called a cusp, where it's kind of like a corner, but it's more, arced as it approaches the corner on each side. The derivative doesn't exist at this point. We also covered vertical tangents, where if you have a vertical tangent, the derivative won't exist at that point. And we discussed the first one in great detail using the definition. We discussed the third one in a little detail, actually using the power rule. But we didn't discuss in any detail the second one. And this problem 3 uses a function which has a cusp, which is why I asked you to sketch a graph of this function. So why would a cusp not be differentiable? Well, you can use your tangent lines. On this side, the tangent lines, the slope of the tangent lines approach negative infinity. On this side, the slopes of the tangent lines approach positive infinity. But here we're going to go through the details. So let's look at the details. Well, first, let's sketch this function. Piecewise function, root x for x positive or equal to 0. Root x looks like that. How about root negative x for x negative? Well, what does root negative x look like? Well, root x looks like that. Root negative x is this with a graph transformation. There's a negative on the x. So all x values are becoming their negatives, which causes what happens over here to flip over and happen over here. We also saw that transformation in doing limits as x goes to negative infinity. So we can get the first part of this piecewise function using a graph transformation, the second part using one of our standard graphs, and notice they do happen to meet at 0. And we get a function that looks like this. Any questions about the sketch of this function? So this is also side work showing the transformation for the first part of the function. Remember, piecewise function, it's called piecewise because it's defined in pieces, given pieces of the domain. You know, that may sound incredibly obvious, but I didn't realize piecewise meant it's defined in pieces in that language until like the middle of college. I think it was actually while tutoring something. Someone said, why is a piecewise function? Or what's a piecewise function? And I just said, well, it's a function defined in pieces. And then I realized, well, whatever. So what do we have to do? We have to show that f is not differentiable at x equals 0. Well, I'm going to show two different ways we could do this. So notice, first of all, this is a continuous function, and it does have a cusp. We do know the derivative won't exist in this case at x equals 0. But let's see the details. Which details do I want to do first? Let's do the power rule details first. And then we'll do the definition. So for the corner function, we used the definition. For the vertical tangent, we used the power rule. This one, I guess I'll show both because we can do both here. So notice, using the power rule, f prime of x, I'm going to use the, so if f of x is root x, derivative, that's x to the 1/2, derivative is half x to the negative half, which is also 1/2 root x for x greater than or not equal to 0. That's not defined at x equals 0. Not that that actually matters. So for the, is that I'm going to have to draw this bigger. F prime of x equals 1/2 root x for x larger than 0. So we have that for the one piece of the derivative. The other piece for x on the other side of 0, well, we would need to use a chain rule because inside the square root is now a negative x. How would that change it? Well, let u equal negative x. It makes it differ by a negative. So you get negative 1/2 root negative x. Well, why does this derivative not exist at 0? Well, it's not because we can't make a substitute. It's not necessarily because we can't make our substitution there. Because remember, the derivative is defined as a limit. Meaning, if the limit on the one side is the same as the limit on the other side, then the derivative will exist and it'll equal whatever that value is. I'm going to have to erase this function to do this. So how should we write this? Notice f prime at 0 does not exist. Why does it not exist? Well, let's look at the limit on the right of 0, and let's look at the limit on the left of 0. Well, on the right of 0, the function, or the derivative is defined as 1/2 root x. As x goes to 0 in the bottom, so you could use like a power rule, not power rule, the limit rule with exponents, make this half times x to the half. And as x goes to 0, 1/x goes to infinity, infinity to the half will go to the infinity, and so on. And you get that this goes to a positive infinity. And actually, this is enough to conclude it's not differentiable, but I will show the other side as well. On the other side of 0, the derivative is defined up there. And what is this limit? That's way too many negatives. I can't see this. How are we going to get rid of these? Well, you don't necessarily have to get rid of the negatives. I want to because I can't register that many negatives at once. I'm going to get rid of these negatives by flipping it over the x-axis, which turns it into a limit as x goes to 0 from the right. Of what? Well, the negative 1 doesn't change if we flip x. 2 doesn't change. Negative x changes to a positive x. And this limit is the same as this, but it differs by a negative. So we get a negative infinity. So right here, the derivative at 0 doesn't exist because the limit on the right doesn't equal the limit on the left. Well, because you get an infinity that causes it to not exist. But here, they're very different. And this does confirm our tangent line observation. So any questions about this first way of doing it using power rule? Okay, so let's do it using the definition of the derivative at a point. So another way to do it, so I'll say another way to show f prime at 0 does not exist using the definition of the derivative at a point. The definition of the derivative at a point, f prime at 0 equals the limit as x approaches 0 of f of x minus f of 0 all over x minus 0 equals the limit x approaches 0 f of x over x. F of 0 is 0, so that second part does equal 0. And how do we compute this limit? Well, it's defined on both sides of 0, so we need to break it down at 0. Limit as x approaches 0 from the right of f of x over x. What does this equal? Root x. What am I doing? I need limits. Can't just get rid of limits. So you take a limit. F of x on the right of 0 is root x over x. That simplifies. 1 over root x. That goes to positive infinity. Same reason as the one we discussed before. The bottom will go to 0 on the positive side. Top doesn't change. And limit as x goes to 0 from the left, f of x over x. On the left of 0, f of x is defined as root negative x. And again, there are too many negatives there, so I'm going to get rid of all the negatives, introduce more negatives, but introduce nicer negatives. Flip it around. The y-axis, replace all x's with a negative x. We get root x over negative x, which equals limit x approaches 0 on the right of negative 1 over root x, which is negative infinity. So we have the power rule. So we could have shown using the power rule that the derivative is different on both sides of 0. Or you could use the definition of derivative at a point, like we did with the absolute value, to show that different things happen on both sides of 0. In terms of all the details we've covered, I like the absolute value details the most. But any questions about number, what was this, number 3? So when we defined the derivative we used the interpretation that the derivative measures or gives us the slope of a tangent line. But we also saw in lecture 7.2 that we could interpret the derivative as a rate of change. And the tangent line can also be interpreted as a rate of change at a given point. And we'll see a few times throughout the semester direct applications using the derivative as a rate of change. For example, number 4. For a particle moves along a vertical line, I'm going to draw a vertical line over here, where up is the positive direction. That'll become relevant at some point. So that its position is given by this function. And time we'll assume is always positive or 0. And we're asked a few questions about this. And for some of these questions, the direction will matter. For some of them, it won't directly matter. Part A, at what time does the particle stop? Well, remember, the derivative of a position function tells us the rate of change of position. The velocity tells us the rate of change of position. So part A says, when does it stop? Well, it stops when position is not changing. So for part A, we set our velocity equal to 0. Well, what's our velocity function? 3t squared minus 12 plus 0. We want to set this equal to 0. So you get what? T squared equals 4. T equals only 2 given our domain restriction. Any questions about part A? Okay, part B. On what time intervals is it moving upward? On what time intervals is it moving downward? Well, its movement is going to be tracked by our velocity function, because the velocity function tells us the rate of change of position. It tells us where the particle is moving. Well, it tells us how the particle is moving, I should say. And in particular, it's moving upward when velocity is positive. It's moving downward when velocity is negative. It's not moving at all when velocity is 0. So what should I say? I'll say up when velocity is positive. I'll say down when velocity is negative. And now we have to find these time intervals. Fortunately, we already have where it's 0, where velocity is 0. Velocity is 0 at time 2. So if we want to find the intervals, well, we know our t is greater than 0 axis is going to be broken at 2. So we have to check what happens on both sides of 2. On the left of 2, I'll choose velocity at 1. The velocity at 1 is negative. The velocity at 1 is what? -9. And the fact that it's negative number doesn't really matter. The fact that it's negative is what matters. So I'll just write velocity is negative. On the other side of 2, well, pick a number here. 3. Velocity at 3 is 15. 15 is a positive number. So the particle is moving up on what? It's moving up where the velocity is positive, not including 2, because at 2 it's not moving. But everywhere after 2, it is moving up. So 2 to infinity, I should write that a little better. Up on 2 to infinity with a curved parenthesis. and down on, that's about 0. Moving down where the velocity is negative. Where's the velocity negative? Well, on the other side of 2, we're only considering 0 and positive numbers. At 2, velocity is 0. We don't include that. Do we include 0? Yes. Why do we include 0? Well, the velocity is not 0 at 0. It doesn't go on the other side of 0 until we get to negative 2. But the way I like to see it is just by substituting 0 up here. You substitute 0, you get negative 12. So you get a negative velocity at 0. Any questions about part, what was that, part B? Okay. Part C. Is the particle speeding up or slowing down at time 1? And then is the particle speeding up or slowing down on time at time 3? For these, it is very important to keep the direction in mind. Now, what's going to tell us about how velocity is changing? Well, the derivative of velocity tells us the rate of change of velocity. So the acceleration function tells us about how velocity is changing on that line. Our acceleration function is 6t. So part C. Let's pick time equal 1 first, because 1 is on the other side of 3. What happens at time 1? Well, at time 1, the velocity is negative. We found that in part B. What's the acceleration at 1? The acceleration at 1 is 6. It's positive. What does that tell us about how the particle is moving? Is it speeding up or slowing down? Well, velocity and acceleration, the sign of a velocity and acceleration, have a direction attached to them. Upward is the positive direction. So right here at 1, how should I write this? We're going to keep in mind upward is the positive direction. Right here, I'm going to mark off where velocity is 0. Because at negative 1, or at 1, the velocity is negative. But the acceleration is positive, which means while the velocity is negative, the acceleration is pushing it in that direction, closer to velocity equal to 0. The acceleration is pushing the velocity closer to 0. That tells us the speed is getting lower. Any questions about that one? Okay. What about at time equals 3? Well, in part B, we found that at time 3, velocity is positive. Right here, acceleration at 3, it's positive 18, so it's positive. So what's happening? How's the particle moving here? Well, again, I'm going to provide a visual for velocity. Remember, speed is, it's the magnitude of velocity, but it's measured by how far away the velocity is from 0. It's measured by whether your velocity is getting closer to 0. So here we're going to keep our velocity equals 0 in mind. Velocity is positive. Acceleration is pushing the velocity in the positive direction, which in this case is up. So the velocity at 3 is going farther away from 0. So the speed is going higher. Any questions about part C? Now you can turn this into a general rule using like velocity negative and acceleration positive. If negative and positive, then slowing down. If positive, positive, then speeding up. If negative, negative, then speeding up. If positive, negative, then slowing down. So part C, we looked at 2 specific points. Part D just asks to generalize these using the intervals found in part B. Part D, when is the particle, on what intervals is the particle? I guess that should say on what intervals, like in part B. On what intervals is the particle speeding up? Well, first we'll notice for part D, acceleration is always positive for time greater than 0. Acceleration is 6t. So for positive t, acceleration is always positive. So using the results of B and C, what do I ask first? Speeding up. Speeding up on the entire 2 to infinity interval found from part B. Slowing down on where the velocity is negative and the acceleration is positive, 0 to 2. And do we include 0? This time we don't. Why do we not include 0? Well, acceleration is 0 at 0. Acceleration is 6t at 0. 6t equals 0. The acceleration is 0, means that the velocity is not changing, so it's not speeding up or slowing down. So any questions about that? And it's very useful to keep in mind for velocity and acceleration, especially problems like B, C, and D. It's very important to keep the direction in mind. Which one is the positive direction? Because acceleration or velocity being positive means there's a push in the positive direction. Being negative means there's a push in the negative direction. I guess I'm a minute over. So there will be an office hour. Well, I'm going to send a separate link in a minute. An office hour until 1:15. There is also a homework assignment due, I think I wrote Monday on it. So, the problems on that are important to practice. But, the weather is supposed to probably get better. It's pretty humid out now. So, I hope you enjoy the rest of your Thursday and, spend some good time practicing the homework type problems, because they are pretty important, especially come exam 2 time. So enjoy your day. I will see you next week.
Thank you.
Thank you.